Thank you for watching part 2. This time, I will mainly introduce hardware production. It will start with the continuation of rough enclosure design with 3D CAD introduced in the second half of part 1. The contents to be introduced this time are as follows. Now, let me first introduce detailed design using 3D CAD. In detailed design using 3D CAD, a detailed design is created following the steps below. In the part selection stage, parts are determined based on the functions that need to be included. And the following functions are largely required for this project. The below is the result of selecting the parts necessary to realize the function. In part selection, I comprehensively evaluated not only performance, but also manufacturing cost. In fact, with ingenious design, it is possible to achieve high performance even with inexpensive parts. Next, the selected parts are turned into a 3D model and incorporated into the frame structure. The transparent LCD movement mechanism consists of 2 linear guides and the lead screw. The 2 linear guides minimize play during movement, allowing for precise movement of the transparent LCD. The power circuit for the UV light source is laid out on the linear moving part. Additionally, 2 fans are installed to cool the power circuit and UV light source. A powerful 75-watt class LED is used as the UV light source, and its light was diffused using lenses to eliminate brightness imbalance. The top cover is removable, making it easy to replace the transparent LCD. Furthermore, by providing a transparent LCD stage, I have made it possible to replace it with a different size LCD. In the transparent LCD installation, the LCD is placed on the UV stage and the light in the gap is blocked with light blocking tape. Next, by attaching the bottom panel, it becomes possible to mount various parts. In the video, a transparent LCD controller and a fan are installed. 2 optical sensors are installed below the moving part to observe the position of the transparent LCD. High precision positioning is achieved by using these optical sensors to control the motor. On the left side of the case, there is a main power supply for receiving power from the outlet. On the right side is the main board, which is the center of all electronic controls. At the back are the communication port and expansion terminal. Stepping motors for moving the transparent LCD and for pulling up the build platform are also located on the back. The stepping motors used to raise and lower the assembly platform have optical sensors to monitor rotation. The optical sensor is designed to react once for every rotation of the stepper motor. This ensures that any angular error in the rotation is corrected for each rotation. Additionally, an optical sensor is installed to measure the origin position of the lifting mechanism. Next, the lead screw and linear guide, which are part of the movement mechanism for pulling up the build platform, are attached. This movement mechanism is subject to a fair amount of load, so many machined metal parts were used. The build platform and top plate are also metal machined parts. A transparent panel is attached to the top panel to protect the mechanism inside the enclosure from foreign objects. Next, the UV resin tank is installed. Hook parts for attaching external panels and a touch LCD for operation are mounted on the side of the casing. The external panels are fixed by hooking them onto the hook parts installed on the side of the casing. Finally, the UV top cover is attached. With this, the detailed design using 3D CAD is complete. Now that detailed design using 3D CAD is complete, I would like to move on to design of electronic circuits. The electronic components were determined based on the functions required for the product, referring to detailed design using 3D CAD. To control the selected electronic parts as intended, control circuits are necessary. Therefore, I first summarized what types of control would be required. Summarizing, it looked like the following diagram. It is unrealistic to create electronic circuits that can perform all these controls right away, so I will first create the circuits on a breadboard separately, performing unit tests for each control. Now let me introduce the power supply control circuit. Designing power control is a crucial process for determining how power is supplied to electronic components. To design power control, I first listed the parts that require power supply. Next, examining the driving voltage of the parts revealed the presence of 5 volt, 12 volt, and 24 volt parts. To obtain these voltages, I used 24 volt power supply and step-down DC-DC converters. By using 24 volt power supply and step-down DC-DC converters, power can be supplied as follows. However, this circuit continuously supplies power to all parts at all times. To control power supply, I added MOSFETs to the circuit. The MOSFETs acts as a switch that toggles conduction and non-conduction between DS via electrical signals. By utilizing MOSFETs, it becomes possible to control whether current is supplied or not. By having the PIC microcontroller control the electrical signals of G0, the power supply of the transparent LCD and the one-board computer can be controlled from the PIC microcontroller. Similarly, by having the single-board computer control the electrical signals of G1, the power supply to the stepping motor and expansion terminal can be controlled from the single-board computer. By designing step-by-step this way, the power control circuit was completed. Next, let me introduce control of the operation LCD and control of the transparent LCD. In this case, I needed to control two displays, the operation LCD and the transparent LCD. Since the single-board computer only has one HDMI terminal, the high-resolution transparent LCD is connected via HDMI, and the operation LCD is connected via SPI. SPI is a type of communication protocol and can be utilized from the GPIO terminal of the single-board computer used. By connecting via SPI, additional displays can be added without using the HDMI port. The pins assignments of the SPI connected display adopted this time are as follows. Terminals enclosed in red squares are for SPI communication with the LCD. Other than SPI communication terminals, the remaining pins are divided into two categories as shown below. Green terminals are for power supply, and blue terminals are for LCD control. If reset control is not performed at startup, the LCD will not display even if data is sent via SPI communication. The blue pins control the display reset. This LCD module also has a touch panel, where red terminals are SPI communication terminals for touch coordinates. Blue terminal change voltage from 3.3 volt to 0 volt when the screen is touched. Next, based on the roles of the investigated terminals, connections to the single-board computer and PIC microcontroller were made as follows. The green wire is connected to the single-board computer, and the light blue wire is connected to the PIC microcontroller. Next, I investigated how to control the display contents of the operating LCD and transparent LCD from Linux. Based on this investigation, the library was independently created to switch display content on Linux. And using this library, the two screens are controlled. Similarly, I conducted experiments on acquiring coordinates from the touch panel for the operation screen and created our own library for acquiring coordinates. Next, let me introduce motor control. Stepper motor as it needs to be controlled using 4 wires, which is a bit cumbersome. Therefore, I decided to use the stepper motor driver A4988. The pins assignment of the A4988 is as shown below, and it can be used by connecting as follows. This video is an experiment in which a stepping motor rotates exactly 6 times. Since the angles at the start and end of rotation align, it is confirmed that the rotation was precise. Next, let me introduce control of the UV light source. The UV light source consists of the LED part and the power circuit part. And since the power supply circuit part had a PWM control pin, I used this pin to control the on or off of the UV light. The video shows testing the UV light brightness control. Not only can turn it on and off, but the UV light can also adjust the brightness. Next, let me introduce control of communication functions. The necessary communications are categorized as internal communication and external communication. The diagram summarizing the communication relationships is as follows. First, internal communication between the PIC microcontroller and the single-board computer is necessary for cooperative operation. Next, enabling wired communication between the external PC and the single-board computer allows for automatic setup of wireless connections between the PC and the 3D printer. Finally, enabling wired communication between the external PC and the PIC microcontroller allows for minimal diagnostic functions when the single-board computer malfunctions. Designing communication paths to meet these requirements results in the following circuit. The communication path between the external PC and PIC microcontroller is the red route. Path between the external PC and single-board computer is the green route. Path between the PIC microcontroller and single-board computer is the blue route. The CH340G is an IC chip that converts USB communication to serial communication. With this, the communication circuit design is complete. Finally, let me introduce circuit design for the controlled PIC microcontroller. The PIC microcontroller is responsible for power control, wired communication processing, and monitoring the touch panel. Adding peripheral circuits to the basic circuit of the PIC microcontroller resulted in the following design. By designing the circuits around the microcontroller in this way, I was able to meet all of the control requirements. In this way, each control unit was designed individually, and all circuits were designed in stages. After completing the design of electronic circuits, finally, let me introduce design using PCB CAD. In design using PCB CAD, the circuits created in design of electronic circuits are integrated into a single board. In my previous project, Windows 10 Powered Electronic Dictionary, I manually created the board using a universal PCB. In this production, I will try to generate PCB manufacturing data using PCB CAD and place orders to PCB factories. For this production, I learned and used KiCad, a PCB CAD system. KiCad is a free, yet highly functional CAD software that can be used to design multi-layer boards. Generating manufacturing data with KiCad roughly involves 2 steps. The first step, creating a circuit diagram, involves inputting the control circuit designed in the previous chapter into the PCB CAD. The second step, creating a pattern, is the process of designing the wiring pattern on the actual board from the circuit diagram entered in the previous step. The first step, creating a circuit diagram, is just a monotonous input process for a design circuit. I will mainly focus on the second step, creating a pattern in detail. In the process of creating the wiring pattern, the above points were taken into consideration when creating the pattern. In wiring width considering current, I must calculate the maximum current that flow by referring to the power supply circuit designed in the previous chapter and determine the appropriate wiring width. If the wiring width is too narrow for the current, it may cause overheating and even burning of the wiring pattern. There's a general rule for appropriate wiring width. 1 mm width can carry 1 ampere of current. This image is a portion of an actual wiring pattern, with thicker wires carrying larger currents. In miniaturization through 3D arrangement of parts are arranged in a multi-layered manner to save space. This video shows how parts are being installed in a multi-layered arrangement on the board. By arranging them 3D, nearly all control circuits fit on a single board. In design rules of the PCB manufacturing factory, it was confirmed whether the design adhered to the rules of the factory. Even if the circuit is correct, it may not be possible to manufacture it in the factory if it does not comply with the rules. For example, there are rules regarding the minimum wiring width, and boards containing wiring that is too thin cannot be manufactured. Following these considerations, the below wiring pattern was created. Red indicates the wiring pattern on the front, and green indicates the wiring pattern on the back. Finally, selecting fabrication output from file allows the output of various manufacturing data. Ordering based on the manufacturing data resulted in obtaining PCB like this. It is surprising that such PCB can be made for $5 per 10 pieces. In this way, the design using PCB CAD was also completed. Thank you for watching Part 2. Part 3 will be posted in 3 days. In Part 3, I will introduce the process of manufacturing parts designed with 3D CAD using actual machine tools. If you found this interesting, please subscribe to the channel to receive notifications when Part 3 is posted. Also, I would be happy if as many people as possible could see it, so I would appreciate it if you could share it on social media such as X. Finally, if anyone has anything they would like to tell me directly, please feel free to DM me on X.